Hey, good morning, guys. Today's the last lesson of 9.2 today. Then we're tomorrow you have nothing really to do. Monday you're going to review. Tuesday, yep, there's going to be a formative, or actually, it's going to be a summative quiz. So it is summative. You'll get one try at it. It's going to be in its learning that you're going to have to complete. Sorry for the juniors who have ACT today, but it's just the way things fly. It's not going to be long. So the last thing, like I said, we're going to do 9.2 day 2 for everyone today. And you're either logged in or you're watching this wonderful video. So where we left off yesterday, we left off with seeing all of our characteristics of growth and basic growth and exponential decay functions. And now we're going to compound some dough. Okay, so we're going to look. Helen's opening her first savings account and she's depositing $500. Suppose she decides on a bank that offers 6% annual interest to be calculated at the end of each year. That means we do not have an n in our equation here. And recall, the formula for compounded interest calculated once a year is given by p times 1 plus r raised to the t power, where p is your principal or your initial amount you deposited, and r is your rate. And remember, our rate is 6%, but we never plug percents into equations. They are always transformed to decimals first, and t is always time in year. So what you need to do is you need to write a function, a of t, to model the amount of money in Helen's savings account after t years. Well, that's really not too bad. Bottom line, all I'm going to be doing here is my a of t equals my initial amount's 500, my interest rate is 0.06, and raised to the t. Now, remember, this is a model. In a model a of t, my model after t years, t has to be represented in my equation. So there's my p, there's my r, there's my t. I have to have a variable in my equation to be a model, or we could simplify that down to a really nice usable one there. We could add our 1 and 1 point and our 0.06 together to get there. Well, what we're going to do is you're going to use, I want you to actually do number 2 and 3. You're going to use that model. You're going to use this model right here, and you are going to calculate how much Helen has in her account in number 2 after 1 year and in number 3 after 5 years, okay? So why don't you just hit pause and do that, and I will be right back. So I entered these into my formula there. So I have 500 times 1.06 raised to the first power, and I don't know, some of you might need a calculator for that, I don't know. But it's $530. Well, if she leaves it in there for 5 years, well, the only thing I need to do is I need to change my formula. I need to change t to a 5. So now I have 500 times 1.06 to the fifth power, and that's if she leaves that money in there, gets 6% a year, never makes another deposit in 5 years, she's going to have $669.11. Now, make sure you understand that if we would ever spin this question on you and asked you, how much interest did Helen earn over the 5 years? Okay, she only made $169.11 in interest because she originally put that $500 in there. Okay, suppose the bank decides to start compounding the interest at the end of every 6 months. If they still want to offer 6% per year, how much interest would they offer per 6-month period? Well, if they're going to be paying you a total of 6% a year. Well, what they're going to do is they're going to divide that 6% by 2, because 6 months is a half of a year. So they're going to give you 3% for each 6 months. That's the same as 6% a year. However, you actually make a little bit more money because they're giving you interest at 3% for the first 6 months. And then the second 6 months, you get your second 3% on it, but you're making interest on your interest. That is why it is called compounding interest. You're making interest on top of the interest that they have paid you. All right? So we have John, Betty, Joe, and Lizzie. They were each asked to calculate the amount of money Helen would have in her savings account at the end of the at the end of the year, if the interest was compounded twice a year. Well, who's correct? Express or explain your reasoning. Well, if I look at that, John and Betty, Joe, and Lizzie, they all kind of have different tactics, and John and Betty Joe, well, they have the exact same amount. Well, if you kind of look back to the beginning of this packet, we have that formula for compounding interest. Okay, well, John compounded it differently than Betty did, and Lizzie just kind of went off the rails. Well, John and Betty Joe are correct. Okay, because what John did was John said, okay, the first didn't want to do that. John just says, okay, well, for the first 6 months, okay, here's my initial deposit, and I'm getting 3% on that $500, and then he added that. Okay, now I have $515. Well, for the second 6 months, he's starting at $515. Then he's getting that 3% added to it. He's at $530.45. Well, Betty Joe, she went straight to that compounding interest formula of P times 1 plus R over N raised to the N times T power, where N, remember, N is the number of times compounded twice a year. Notice she's got a 2 in there, and it's at the end of 1 year, so that's why she doesn't have that times 1 there. She's like, I know what that is. Well, Lizzie calculated the interest for the first 6 months correctly. Okay, if Lizzie got rid of this 2, okay, this would be the interest for the first 6 months. Yep, she did that, but then she's like, oh, I get that again. No, she didn't put another $500 in there, at the end to kick that up. So that's who is correct. Well, number 6, what I want you guys to do is I want you to use Betty Joe's technique. I just showed it to you. It's right here. Use Betty Joe's technique to calculate the amount of money Helen would have in her savings account at the end of the year if interest was compounded four times a year. That would be quarterly. That means that N and that N, those are 4. That's compounded quarterly. And they are still going to say, hey, I'm only going to put it in there for 1 year. And then what would you change in number 7? Or what would you change in number 6 if Helen would have her savings account, if she kept the money in her savings account for 10 years and it was continued? Go through and answer 6, 7, and 8, and then we're going to turn on to 9. So why don't you hit pause and do 6, 7, and 8. All right, so we're back, and if we use Betty Joe's technique to calculate the amount of money Helen would have in her savings account at the end of the year if interest was compounded 4 times a year, well, that just means all I am doing is I am changing my formula that I had before up there. See that N? What I got to do, it's still in there for 1 year, but now N is 4. So now, because it's calculated 4 times a year, notice right up here in this little corner, okay, she's going to get paid interest 4 times 1, 4 times in that year, okay? And then let's say, well, what would you change in your equation in problem 6 to calculate how much Helen would have in her savings account if she kept the money in there for 10 years? She didn't put any more in, but now notice this little guy right there, that stands for 1 year. We're going to replace that. We're going to replace that with a 10 for T because it'd be in there for 10 years. And if you look at that, that's going to be 4 times 10. She's going to get paid interest 40 times over that 10 years, okay? And then what they want you to do is they want you to write a function to model the amount of money in Helen's savings account at the end of T years, compounded N time. Notice, this is telling me 2 variables in my model because I can change T, right? I can change T at any time, and I can change N as well because interest might be compounded once a year, twice a year, 4 times a year, 12 times a year, maybe once a week. If it was every week, that'd be like 52. So there's our model. And our model is going to be 500, because that's how much she put in there, times the 1 plus, that's always a 1 plus. See, this 1 plus is always in there. And my rate was 6%. Yeah, good luck with that. You're never going to get 6% interest in your savings account, but we can think about it. And we're going to take that 6, and that 6 is going to be divided by however many times they're going to compound your interest. Okay, so if it's twice a year, they're going to pay you 3% 2 times. Okay, and that's how they get that interest rate in there. So then what we're going to do is determine the amount of money in Helen's savings account at the end of 3 years. 3 years, if she compounds her interest twice a year. Okay, well, compounding twice a year, interest twice a year, that means N is 2. And if it's in there for 3 years, that means T equals 3. So I replace an N gets a 2, a T gets a 3, and I plug that little bugger in there. And it's A of 3, that's my account balance in 3 years if it's compounded 2 times per year times my 3 years. Oh, check it out, she's going to get interest 6 times. Her account balance is going to be $597.03. Well, what if they paid you interest every month? Well, now I'm still in here for 3 years. T is still 3. But now they're saying, hey, go in there and change N. What is going to happen? Now that's no longer a 2. That's no longer a 2. It's going to be a 12. And if they pay you interest once a month for 3 years, think about it. This exponent multiplied together in the next problem, that's going to end up being 36 because that's how many times they're going to pay you interest. So my A of 3, my account balance in 3 years, if they pay me interest 12 times a year, ooh, it's kind of how it works out, I'm going to have $598.34. Not a little, not much more, but hey, it's more. Take it where you can get it, right? Well, what if they paid you interest daily? Yeah, they don't do that, but what if they did? This is leading into a big topic. Well, now N is 365. It's still my account balance after 3 years. That's what A of 3 means. Now they're paying you lots of interest here, or they're paying you interest many times, but notice the rate at which they're paying you is 0.06 divided by 365. That's not much, but it's still more. It's $598.61. Hey, I think I would absolutely love to be paid interest daily in my savings account if I could, okay? So what effect does the frequency of compounding have on the amount of money in her savings bank, in her savings account? Well, that should be pretty obvious, guys, because as N got larger, so did the account balance. It wasn't a ton of money, okay? It was not a lot, excuse me, but it did get more. Hey, this makes you happy for Thursday, isn't it? We're going to skip number 11. Why? Because we're just going to bomb right past that bugger, and we're going to apply what our easy E is. Oh, easy E. Doesn't that sound fun? Easy E. E is a special thing in this world. Very special thing. So what we're going to do is we are really going to put together a fictitious example to figure something out here. Well, what do you mean figure something out? I got to get my stuff all lined up on there. We're going to say, imagine Helen finds a different bank, and yes, this is never going to happen, but that bank, oh, lo and behold, that bank is going to offer 100% interest, okay? And what we're going to do is we're going to complete the table below to calculate how much Helen would accrue in 1 year, every time it's 1 year, for each period of compounding, if she only deposited $1. So notice my T every time, everywhere down here, okay, T equals 1. The only thing that's changing is my N, okay? Notice, compounded yearly, N equals 1. Semi-annually, that implies 2. Quarterly, hey, there's 4 quarters in a dollar. Monthly, you know there's 12 months in a year. Okay, so that's what we're going to be doing. We're going to be compounding that. Her initial investment, okay, that's her P value. That's this first 1. And that's going to get multiplied times this formula of 1 plus my rate. Ooh, 100%. That means your decimal shifts. That's why there's a 1 up there. And we're going to divide that by the n raised to the n times t power. And in this case, both n and t are 1. T's 1 all the way down this column, okay? And then we're going to say, hey, well, if they pay her interest once a year, well, if she gets 100% interest, hopefully that makes sense. Well, if she deposits $1 at the end of the year, she's going to have $2. Duh. Well, what if they paid her interest semi-annually or twice a year? Well, this is the beauty of compounding interest. Well, that means she's actually going to be getting paid 50%, except twice, right? So we're going to type this into our calculator, and her balance is now $2. Two whole dollars and 25 cents. Well, what if it's quarterly? Well, now n is 4, so I just switch my 4, type it in, $2.44. Well, now if n is monthly n is 12, so I replace n with a 12. Now she's up to $2.61. What I want you to do is I want you to figure out the rest of this table because it was kind of cool, you know. As n got bigger, we made more money. That's what we want. Well, think of this. Weekly, there's 52 weeks in a year. Daily, there's 365. We're going to go with days in a year. Hourly. Ooh, how many hours are in a year? Well, that would be hourly 365 times 60 to get 8,760. Well, how many minutes is that? Well, if there's this many 8,760 hours in a year, if I take that times 60, now I got minutes. There's 525,600 minutes. Well, how many seconds are in a year? I know you don't care, but if there's 525,600 minutes in a year, if I take that times 60 again, there's 31,536,000 seconds in a year. Well, we are going through, you are recomputing this, and you are finding how much she has in her balance, okay? So why don't you hit pause and go finish that up, and we'll be there. As I cruise through here, hopefully you found out, you can see my values I got there. All my values are there, and what it looks like is, whoa, something's crazy. Notice I did round all these to 2 decimal places because we are talking about money, but these last few here, okay, because they all rounded to the same number, I kept a bunch of decimals just to show how close they are, okay? And what's happening is it sure appears that this is converging to a particular amount over there, a particular balance, okay? Make an observation about the frequency of compounding and the amount that Helen earns. What is happening? Well, what is happening? As n gets very large, the amount finally quits growing, right? Well, the amount Helen earns approaches is actually an irrational number called E. E is a number, think of pi, you know, what's that? 3.14159. It keeps going, right? Now we have to know what E is. And there's this whole concept of E with this whole big portion here of our interest formula. This is the ugliest part of that interest formula. And as n goes to infinity here, what happens is n gets to infinity. This value that this equals converges to this irrational number E. Now, it's irrational because that number never repeats, it never terminates, it's just like pi, and it's such an important number, mathematicians called it E. It's a little lowercase e. So anytime you see that, E's not a variable. E is that number that we are talking about there, okay? And we use it for continuous growth, okay? Well, what's continuous growth? Well, it's like population growth, and I'll get to there. I'm not going to read all this, but we have the following graphs here are sketched on the coordinate plane. We have 2 to the x, 3 to the x, 10 to the x, 3/5 to the x, and 1.3 to the x, okay? So we can see we have actually 4 growing functions in here. Well, there's 4 growing functions, but there's only 2. Son of a biscuit liquor. But there's only 2 written here, okay? And what am I looking at? Well, Consider the function m of x equals e to the x. Use your knowledge to approximate the value of e and sketch its graph. Explain your reasoning. Well, what I would certainly think here is I would certainly think, well, m of x, well, we just kind of like very newly learned what that letter E stands for. So if I kind of looked at, put this in respects to what they just gave me, this is really kind of like 2.71828 blah, 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 raised to the power of x. Notice this base right here, right? Notice where is it? It's right kind of between a base of 2 and a base of 3. So I would totally expect that this m of x is going to graph between these two. Well, I can totally see the black one is my steepest one. So then I have two more. I have 2 to the x and 3 to the x. So which one is my e in there? Well, I have more than one actually, because this is a growth too. But that means my e to the x is going to actually end up being, so here's my steepest, that's black. Here's my flattest, so that's green. Okay, so I have red and blue. And I can see this is going to be red, this is going to be blue because of the bases that are on there. So I know that my E is going to kind of come through and it's going to grow and it's going to grow between those. It's not going to grow as fast as the red one, but it's going to grow faster than the blue one. It's not going to be as close as it is there. It's just my calibration is all goofy here on my smartboard. So what do they want me to do with this now? Well, using functions of f of x equals x squared and or 2 to the x and 3 to the x and e to the x, find values of f of 2 and g of 2 and use these values to estimate m of 2. Use common math sense and not a calculator to estimate m of 2. Then use your calculator to find m of 2. Well, bottom line, if I took f of 2, and here's my f of x, so that's going to equal 2 squared, that's going to be 4. And if I took g of 2, okay, here's my g function right here, that's going to equal 3 squared, that's 9. Okay, m of 2, well, that's going to be e squared. What is this e you speak of? I know this is going to equal somewhere, and I know it's going to be between there, okay? And it's probably going to be closer to 9 than it is 4. How close? I don't know, and I'm saying closer to 9 because e is actually 2.71828, blah, 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 blah. And this number is much closer to 3 than it is to 2. Therefore, when you square it, its output is going to be closer to 9 than it is 4. And when you type it into your calculator, m of 2 equals, there is that e symbol on your calculator, squared, and that's going to approximately equal, and whenever you hit the e button on your calculator, it will only allow you to put an exponent in, because that's how special the function is. And we get 7.389-ish, and check it out, it was way closer to 9 than it was 2. Okay, just about the last page, okay, so populations keep growing and growing. So like I said, back here, this E thing is continuous growth. It's used for It's used for continuous growth. Well, what continually grows in our world? Well, continuous growth would be like population growth, okay? And any time in an equation you see that E in there, that is continuous growth. Okay, continuous growth. And the little formula there, that little n sub naught, that little n naught, that's my initial population. That is like when I'm thinking of y equals a times b to the power of x or something, that little n naught, that's just like my a. That's my starting value, okay? That's just like when I'm thinking of my account balance in terms of time equals p times 1 plus r over n raised to the n times t, okay? Well, what happens is this p, that is like my n naught, but in continuous growth, all of this business, see, they're going to grab my r and they're going to pop it out here with my t, but all this business actually ends up turning into e when I'm thinking n going to infinity, all right? I'm just going to leave it at that. R is my rate of growth. I'm going to get rid of that stuff there quick. R is my rate of growth as a decimal, and t is the time. Could be defined in years, days, or hours, etc. It just depends how what your word problem's doing, because you might be doing bacteria growth, and the bacteria grows faster than population. And n of t is the population after t times. So why do you suppose E is used as the base here for this population growth? Well, here's why. Because populations continuously grow. They're growing daily, hourly, secondly, okay? Not just at convenient times like interest does, okay? Populations are always growing. How could you use this formula to represent a decline in population? Well, because my rate is right up here in the R, my rate's right up there in the exponent, how I would do that is my R, my rate of growth, would be negative in value. I would, if my population's decreasing at 3%, I would probably use a negative 0.03 in my exponent, okay? And population of Fredericksburg, Virginia. Really, Fredericksburg, we won't use that, that's okay. It was approximately 19,360 in the year 2000, and it's been growing at a rate of 2.9% each year. Well, use the formula and for population growth right here to write a function to model the growth of Fredericksburg. Well, now I'm taking this because it's population growth is always continuous. That's why we're using E. And if we're writing a model, remember, we must have a variable in the equation. Well, n of t, population of Fredericksburg at any time t is going to be, well, what was the initial population? 19,360. And it's a continuous growth because it's population growth. So that's going to be a base E exponential. And that's going to be raised to my percent. Well, 2.9%, well, that equates to 0.029 as a decimal, right? So that's 0.029 times however many years I'm talking about. See, n, my population n in terms of t, so I'm going to plug in a t. So what are we going to do? Well, use your function to predict the population of Fredericksburg in 2013. Well, it's kind of important back here that I thought, oh, in the year, my starting population of 19,360 was in the year 2000. So this is when t equals 0 is the year 2000. Really important thing to know. That's when I'm using my function, because if I want to go to 2013, well, remember, t equals 0 represents the year 2000. So t equals 13 would be 13 years past 2000. So that would be t equals 13. So we want to find n of 13, and we're going to find that by saying 19,360 times e to the 0.029 times 13. And this is going to spew out, and we are going to round to the nearest person. I'm going to say 28,225 people. Okay? Well, that's what the population is going to be 13 years from now in 2013. Okay? What does your function model give you for the population of Fredericksburg in the year 1980? Well, remember, this is for the year 2000. If I go back to the year 1980, I'm subtracting 20 off. So t equals negative 20 is going to represent the year 1980. So I'm looking at n of negative 20 in function form, And what's that going to give me? Well, that's 19,360 times e to the 0.029 times negative 20. And what happens, this backs up my population. And I'm going to say, oh, it was about, I'm just going to round it off. And I forget how I rounded, but you can round up or down, 10,839 or 10,840 peeps. That's about what the population was. I would accept either one of those rounding up or down, okay? Now, the last thing you're going to do is you're going to use a graphing calculator to estimate the number of years it would take Fredericksburg to grow to 40,000 people, assuming the population trend continues, okay? Try on a graphing page. I'm trying to find my, I gotta hit pause here a second. So rather than using such big numbers when I graphed it, okay, I took this advice right here, or you can change your equation above in terms of thousands. So if I did that, well, now my initial amount is going to be 19,000 or 19.36, because if it's in thousands, remember, I would just take it times 1,000. Well, if I redefine my function, my n of t is going to equal 19.36 times e to the 0.029 times t, right? And what we are doing is we are trying to predict when n of t, when is my y going to be about 40,000 people? And if I have already converted my equation into thousands of people, I don't want to turn it into 40,000. I want to see it 40. Well, why would I want to do that? Well, I'll show you. You have no idea how to solve this yet. You're going to graph this in dead mouse. You're going to graph this in dead mouse, okay? And you're going to find their intersection. So here is the graph of, the blue one is the graph of my function growth. The red one is the graph of 40,000. Now remember, I even put labels on here. My t-axis, t, or my x-axis, okay, is years since 2000. So here's the year 2000. Here's the year 2005. Here's the year 2010, okay? And I changed this so I could go 0 to 40. If I had 40,000, I'd have to go 0 to 50,000. That really makes my y-axis jacked up. And my y-axis is reflecting population in thousands, okay? So I find that little intersection right there. And I'm like, oh yeah, I'm going to track that down. How much is that? I don't know. But I know Desmos will tell me it's at like 25.023 years. Okay? What am I going to do? How long is this going to take? Well, so T is approximate, that's pretty dang close to 25, approximately 25 years. Okay? And if it's 25 years, remember, I'm going to have to add that. So I'm thinking the year 2025, the population is going to be 40,000, because remember, this is in thousands. Okay? And sorry for the length of this. However, I have one last thing for you here. I'm going to check your understanding. And why don't you hit pause and see if you get this right. I'm going to be back with the answer. Okay, I'm back for the attack. Well, Jan invested $5,000, so that would be your P. In an account savings, in a savings account for 6 years, well, that means T equals 6. The bank pays you 2% compound. Well, that means R is 0.02. Compounded monthly, that means N is 12. At the end of 6 years, well, there's that T again. How much would Jan's investment be worth? Answer? Well, there it is. I gave you the answer, but I want to be able to plug this in. There's my P, there's my R, there's my N, there's my N, there's my T. The key is, I know most of you will be able to plug things into the formula correctly, but the key is, can you plug it into your calculator correctly and make sure you're getting the correct answer is the question of the day. Hey, again, apologize for the length of this, but this is pretty important stuff. And hey, have a great rest of your day.